So today what I'd like to talk about are energy diagrams, diagramming out how reactions occur, and talking about transition states, those species that occur as at an energy high point in the step of a transformation of reactant to intermediate or intermediate to product, or the direct transformation of reactant to product. And then we'll be discussing a little bit about reaction rates and rate equations. Some of these are ideas that you got in general chemistry, but just as in this class we've been returning to a distinct organic flavor, we'll be doing the same thing here. We're going to be considering two chemical reactions today as examples, as archetypes. And these reactions are going to be reactions that you'll be learning more about in Chapter 7. We'll be concerning ourselves with, or looking at, the reaction of cyanide with iodoethane, which is an example of what you'll learn is called an SN2 displacement reaction. And the reaction of cyanide with bromotriphenylmethane, and what you will learn is an example of what's called an SN1 reaction, SN1 displacement reaction. I used at least one of these reactions in our previous lecture, so let me write this out again. So we talked last time about the reaction of iodoethane with cyanide, and of course that cyanide would be part of a cyanide salt, like sodium cyanide or potassium cyanide. And the product of this reaction is propane nitril plus iodide anion. Now, this reaction, what's occurring in this reaction is the cyanide anion is coming along to the iodoethane and literally pushing out, displacing the iodide. I'll show this with curved arrows. So here's the carbon-iodine bond represented by the CH2I. I'm going to write the cyanide anion, and as you will see more and more as we begin to write organic reactions, because molecules are big, because there are many bonds and lone pairs of electrons, often I'll just show lone pairs of electrons right at a reactive site. And so what's occurring is the electrons on the cyanide are coming and attacking the carbon. And remember, we always show curved arrows as flowing from the electrons to atoms or to bonds. And we push electrons onto iodine to form our iodide anion. Now I'm going to contrast this with the reaction of bromotriphenylmethane, PH3CBr. I could do the iodide here. It doesn't really matter whether I have the bromide or the iodide. I've just chosen the bromide for iodine. And I'll still take cyanide anion. And in this case, we see a very similar reaction. The cyanide kicks out the bromine. It's a substitution reaction. We substitute cyanide for bromine. We get bromide anion as a result, as a product of this reaction. All right, one thing I should do at this point, before I have a benzene that's connected at one point, it's C6H5, but let me draw this out explicitly at least once. What you're going to learn in the next chapter, so here's the compound. What you're going to learn in the next chapter is the biggest difference between the compound on the left, the iodoethane, and the bromotriphenylmethane is not the bromine versus the iodine, but rather that your carbon is a tertiary carbon in the case of the bromotriphenylmethane, and it's a primary carbon in the case of the iodoethane. And for various reasons, this does not allow the reaction, the carbon being tertiary here, does not allow the reaction to proceed in a single step. Instead, the reaction proceeds in two steps by way of a carbocation intermediate. It's a big mouthful to swallow, so let's break this down into bite-sized pieces. What's happening over here in the first step is that our bromotriphenylmethane is breaking apart, is ionizing into a triphenyl methyl carbocation and bromide anion. I'll write this as an equilibrium. Now again, all of these species are new, so let me write this out in a little bit more detail for you. The intermediate now is 3 benzene rings on a carbon in which there's a carbocation. There are 2 reasons why this carbocation can form. One of them is a little more obvious than the other. The little bit more obvious reason in this case is resonance stabilization. You can write many resonance structures that spread out the positive charge. The other reason, which we're going to be coming back to in chapters 7 and chapters 8, is that tertiary carbocations, carbocations in which you have 3 carbon substituents on the carbon bearing the positive charge, are much more stable, much easier to form than primary carbocations, carbocations in which you have 2 hydrogens on the carbon with bearing the positive charge. Okay, so in the first step of this reaction, we ionize this molecule. If I wanted to write this out as a mechanism, I could write this, and again, I'll just give you an abbreviated mechanism. Bromine leaves, we show a curved arrow to show that bromine leaves taking its lone pair of electrons, and that's going to leave a positive charge on the carbon atom. And then in the second step of the reaction, so here's step 1. In the second step of the reaction, our triphenyl methyl carbocation reacts with cyanide anion. To form a new carbon-carbon bond to form our product. And again, if I wanted to give you an abbreviated mechanism, it's essentially the reverse of this step. In this step, electrons left from a bond to go on to bromine to give bromide anion. In the next step, here's our carbocation, here's our cyanide anion. Electrons flow from the cyanide anion to the carbocation carbon, and I'll draw that with a curved arrow again, to form a new carbon-carbon bond. Thoughts? How would I, great question. So we've written three different ways of thinking about this reaction here. The question is, how would I write it? If I'm just showing the overall reaction, I'd write the first equation. If I were trying to express the steps that were involved, I'd write these two equations. And if I were trying to show in great detail, if I said, for example, on a quiz or an exam, show every atom, every lone pair of electrons, every bond that's involved, then I might show the mechanism in great detail. Then I might write it with this and perhaps even more detail, writing even a triple bond from a carbon to a nitrogen. So there are many levels of understanding and many different aspects that we can look at. Now let's take a look at an aspect of the first reaction. Let's see how we can diagram out how that reaction occurs and then contrast the second reaction. By the first reaction, I mean the iodoethane reaction. So in the case of the first reaction, we can write an energy diagram. And basically what this is trying to show is the energetics as the reaction proceeds. In an exothermic reaction, in a reaction that releases heat, a reaction that tends to, quote, go, the energy goes downhill. In other words, the reactants have more energy than the product. In the reverse of the reaction that goes uphill, a reaction where the equilibrium lies to the left instead of to the right, then you'd have things going uphill. But for a typical reaction that goes, we go downhill. So, this is a horrible graph here. Let me try to write my axes a little bit more orthogonal. So we can put energy on our y-axis, and then on our x-axis we can express the course of the reaction. The term that we use for this is the reaction coordinate. You can think of it as progression over time, or bond length as it's made and formed, or simply as we're going from the left of the equation to the right of the equation, what's happening. So let's do this for iodoethane and cyanide. Here's our reaction coordinate. On the left, I'll express our reactants. Our reactants have a certain energy. Our reactants, of course, are iodoethane and cyanide. Our product, in the case of this reaction, are propane nitrile and iodide. As I've said, they're lower in energy, so I'll draw a line indicating the presence of the products at a lower energy, CH3, CH2, Cn, and I-. And now we're proceeding from the reactants to the products without the formation of any intermediate. In other words, we are simply going. As that bond to the iodide is breaking, the cyanide is coming and forming a bond at the same time in a concerted fashion. We go over an energy hump. And come down to the product. So what's happening is the cyanide is getting closer, 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 closer. The iodine is getting further, further, further away. As we proceed, at some point, we have a partial bond to iodine and a partial bond to cyanide. The iodide continues to leave. It goes further and further and further away. The cyanide gets in closer and closer until it's at the carbon-carbon bond. We call the highest energy point on this transition from reactants to intermediates, intermediates to products, or directly from reactants to products. We call the highest energy point the transition state. transition state is the term then that we give to the arrangement of atoms and molecules at that point, at that highest energy point, as we're proceeding from reactants to intermediates or intermediates to products. The transition state for this reaction is going to look something like this. As I said, the cyanide is coming in. We're forming a bond, we're breaking a bond, and at some point halfway between, and let me write this in a way that really shows the bonds being made and broken. So I'll put the methyl group off on the side. So at the point of the transition state, we have a partial bond to cyanide. We have a partial bond to iodide. We have part of our negative charge, not necessarily quite half, but somewhere around half, on the cyanide, part of our negative charge on the iodide, partial bonds. This species exists for a fleeting instant. This is not an intermediate. This is not something that you can even put into a bottle for a millisecond or a microsecond. This is something that lasts as long as a bond vibrates. The transition state exists for about 10 to the minus 15th seconds. On a molecular time scale, the blink of the blink of the blink of an eye as that cyanide is pushing in and the iodide is coming out. So that's what our transition state is. That's that point on the reaction coordinate diagram as the bonds are making and breaking. In this case, the transition state is on the course directly from reactants to products because the reaction proceeds with no intermediates. But in the next case we look at, we'll see two transition states, one as we go from reactant to intermediate, and another as we go from intermediate to product. Let's take a look at some of the other features that are shown on this diagram here. So what else is represented? The height of the transition state tells us how high an energy barrier we have to overcome. A transition state that's higher in energy relative to our reactants means we need more energy to make that reaction occur. We call that energy the activation energy, and as I said, it's the difference in energy between the transition state and the reactants. And I'll write this as EA. We're being a little bit loose in our diagrams between energy in a generic term, enthalpy, heat of reaction, free energy, and we can get away with it at this point in the course. And in a later course or in a physical chemistry course, you might want to be a little bit more rigorous about this. All right, so this is the amount of energy that you have to put in to make the reaction go. If I did something and changed the structure of the molecule, for example, made a, let's say, a chloride instead of an iodide here, we might raise the energy, the activation energy. That means we're going to have to put in more energy to get over that energy barrier. Now, there's another energy that's expressed in this reaction, and that's the overall energy of reaction, whether energy is released or energy has to be put in, whether the reaction is exothermic or endothermic. And if we want to play loose between enthalpy and free energy, whether the equilibrium lies to the right or to the left. This reaction is downhill. Energy is released. The difference in energy between reactants and products we can think of as delta H naught, as the enthalpy of reaction. Downhill means that it's negative. Negative is good. It means energy, specifically heat, is released. Uphill is bad. It means you have to put in energy. It means that the equilibrium lies to the left instead of the right. And so that diagrams out this reaction between ethyl iodide and cyanide. Now, let's take a look by comparison at the reaction of bromotriphenylmethane and cyanide. And so I'm going to draw an energy diagram for that reaction on the left-hand blackboard. All right, so same idea. I'm going to draw some coordinates. Energy. Questions or thoughts? Yeah. Great question. Is there a way to tell from a reaction if it's a single step or a double step? We're going to be learning a lot about that in Chapter 8 and Chapter 7. A very good rule of thumb for substitution and elimination reactions is if an alkyl, and you're going to be learning lots more as we move through subsequent chapters, but we're just going to start with alkyl halides and nucleophiles and bases in Chapter 7 and Chapter 8, where we learn about substitution and elimination reactions. A very good rule of thumb is that a substitution or elimination reaction on a primary halide proceeds in a single step, and a substitution or elimination reaction on a tertiary halide proceeds in two steps. And we call the substitution reaction that proceeds in a single step an SN2 substitution reaction, and the elimination reaction an E2 elimination reaction. The one that proceeds in two steps we call an SN1 substitution for the substitution, or an E1 elimination. And the reason for this comes to two things that we're going to see more in the subsequent chapters, that the carbocations form more easily in the case of a tertiary carbon than a primary carbon, and also the steric hindrance, the crowding of a tertiary center makes it very difficult for a nucleophile or a base to get in close enough to do these reactions, so they proceed in two steps by way of the carbocation intermediate. Now, the thing that confuses the heck out of students is, oh no, well, he talked about primary, he talked about tertiary. What didn't I talk about? Secondary. And things get even more complicated in secondary. And this is the reality of chemistry. Often when you mix two different chemicals together, several different types of reactions can occur in varying amounts. And so we'll spend time talking about secondary and when you get SN1 reactions, when you get SN2 reactions, when you get E1, when you get E2 reactions. And this is both the beauty and the complexity. We'll also spend time discussing the stereochemical force in these reactions. Other questions?
Does activation energy vary with temperature?
Okay, great question. Does activation energy vary with temperature and pressure? Not much, a little bit. But what varies a lot, particularly with temperature, is how much energy, this is a great question, how much energy is available to the molecule. So when I heat the reaction mixture containing sodium cyanide and ethyl iodide, I put in more energy. The reaction, more of the molecules at any given moment have enough energy to make it over that energy barrier to form the transition state and proceed to products. Other questions? These are good questions. Energy diagrams are awesome. All right, so let's energy diagram out our second reaction, the reaction of bromotriphenylmethane with cyanide. All right, so again, we know that this reaction proceeds. The equilibrium lies to the right. The reaction goes downhill in energy. So I have a good starting point. I can write my reactants on the left, bromotriphenylmethane on the left with cyanide, and I can write my products on the right. But now we go through an intermediate. That intermediate's a carbocation. And I can already guess, in this case, that that carbocation isn't too happy. It doesn't have a complete octet. It doesn't really want to exist without 8 electrons around it. So it's high in energy. So on this diagram, for this particular reaction, I can immediately infer that our carbocation is significantly uphill in energy. I'll draw it up here. And of course, in addition to the carbocation, we have our cyanide in the whole gamish, and we have our bromide, and that's what happens at the end of step 1, this mixture. And so that is somewhere up higher in energy. Now, as we proceed from our reactants to our intermediates, we go over an energy barrier. That energy barrier is, again, a transition state. I'll call it transition state 1. And you'll see 2 ways that people designate transition states. One is they'll refer to them as transition state, or TS if they're short on temperature. The other way is they may use this little double dagger. That little double dagger is another way that people designate a transition state. There's also an energy barrier for cyanide getting back together with bromide, with triphenylmethane carbocation. In this case, as is often the case in downhill reactions, the energy barrier is higher for breaking apart than it is for coming together. If you want to think about it this way, you can see that the cyanide is happy, very happy, to get together with the carbocation because we go downhill in energy relative to the bromide. And so often, the energy barrier will be lower for this step occurring. So I'm going to show that by drawing a lower barrier, saying, yes, there's still some barrier. You've got to push some solvent aside for those 2 ions to get together. but it's not as big a barrier. So this is our second transition state. I'll call it TS2. Since the first step has a higher barrier, since the height of the transition state, the energy of the first transition state, is greater than the energy of the second transition state, we call the first step the rate determining step. In other words, it's all downhill from here. The hardest part is breaking that bond. After we break the bond to bromine, cyanide and the carbocation will find each other and they will recombine. The rate determining step, we'll see the implications in a moment when we discuss rate equations. But we can diagram out the energies that are involved. Here's the activation energy for our first step. I'll call this EA for step 1. And we have just a tiny little activation energy. I'll call this EA for step 2. And finally, if we're looking at this reaction diagram, we also want to think about how much overall energy is released, regardless of the pathway, regardless of the path that the molecules take. The overall energy, the enthalpy of reaction, is the difference in energy between products and reactants. And so we have this downhill delta H naught. So it's negative. Thoughts? Questions?
So is the intermediate step always going to be higher in energy than also the reactants and products?
What's the question?
The intermediate energy for the intermediate is always going to be higher?
Great question. Will the energy of the intermediate always be higher than the energy of either the reactants and the products? Not always. There are some reactions where we hop down to one intermediate, and then with more time, hop further down to another intermediate. So not always. And sometimes you have to look at the energies of the bonds being made and broken. In a case, and right now for Chapter 7 and Chapter 8, we're going to be studying a lot of reactions where when we form intermediates, those intermediates are carbocations. In general, carbocations are high in energy. In general, any intermediate in a reaction that involves the formation of a carbocation is going to be higher in energy than the reactants or the products. Well, sometimes you'll have to figure it out, and sometimes you'll be given it. But a good rule of thumb is carbocations are higher in energy than most other things. They will, in general, be relatively high in energy. Another good rule of thumb is a reaction where the equilibrium proceeds to the right, a reaction that wants to occur. That reaction is going to be downhill in energy. A reaction where the equilibrium exists to the left, where it doesn't want to occur, that's going to be uphill. And of course, downhill means the products are lower than the reactants in energy. Uphill means they're higher. Other thoughts and questions? All right, so as I said, step 1 is the rate determining step because it has the highest energy barrier. specifically because it has the highest energy transition state. In this particular example. So what does that mean? It means it's the slowest step. Can the rate determining step be step 2? It could indeed, if the reaction had a higher barrier for the second step. Often, when a reaction is downhill in energy, often the second step is going to be faster. And this is something called the Hammond postulate. It basically talks about what transition states look like. If the transition state really wants to form, it's going to be easy to form. And usually that occurs in a case with a downhill reaction. Let's take a look at those transition states. So here's what transition state 1 looks like. In transition state 1, we're breaking the bond to the bromine. The bond has gotten longer. We're starting to develop a positive charge on the carbon. Delta positive indicates a partial positive charge. We're starting to develop a negative charge on the bromine. We haven't developed a full negative charge. And we have elongated the bond as we're pulling them apart. And this is the point at that high point there. As they pull apart more, solvent gets in, it stabilizes the carbocation, it stabilizes the bromide anion, and it becomes a little better as we get to the intermediate. In the second transition state, I'll call that TS2, now the cyanide is coming in. We formed a partial bond between cyanide and carbon. We have a partial positive charge on carbon, a partial negative charge on cyanide. So, you very aptly asked for an example of a reaction where the second step has a higher barrier. And believe it or not, you and everyone else in this room already knows of one example. That example is already staring at us on the blackboard because every reaction, at least nominally, has a reverse reaction. And the reverse reaction proceeds by the exact same mechanism, but in reverse. So if we look at the reverse reaction, of the product plus bromide anion, I'll draw this as an equilibrium lying way to the left. The reaction diagram, the energy diagram for this reaction, it's an uphill reaction. The equilibrium lies to the left. Our reactants are over here. Our products are here. The products, of course, are these. The reactants are these. The intermediate is exactly the same as we have over here. It's higher in energy. And now, this reaction has a lower energy barrier, a lower transition state for the first step than it does for the second. Because, of course, all I've done is flip this around. The delta H naught is positive for this reaction. Our activation energy is higher for the second step, or more specifically, the second step is the rate determining step. And the reaction goes like so. All right. Rates of reactions. So just as we've done, we'll take some ideas that you've seen in general chemistry, and we'll just put a little bit of an organic flavor on them. We'll just apply the ideas that you learned in general chemistry to the organic chemical reactions that you're looking at. The rate of a reaction is equal to some rate constant K, which is going to depend on how high your energy barrier is, how high the height of the transition state is in the rate determining step, times the concentration of the reactants, but more specifically, the reactants involved in the rate determining step. In other words, after the rate determining step, it doesn't matter the concentration of reactants. So our one-step reaction, our SN2 reaction that we looked at first, our reaction of ethyl iodide, iodoethane, and cyanide, the rate is equal to K, the rate constant for that particular reaction, times the concentration of the reactants involved in the rate determining step. Well, what's involved in your rate determining step? We have ethyl iodide in the rate determining step. And perhaps I should say, just so I clarify it, I'll say species, because of course they might be intermediates as well. So we have ethyl iodide in the rate determining step, and we have cyanide in the rate determining step. What does this mean? You double the concentration of ethyl iodide, you double the rate. You double the concentration of cyanide, you double the rate. But now let's take a look in comparison of the reaction of bromotriphenylmethane with cyanide. In the case of bromotriphenylmethane, the rate determining step is the first step. The rate of that reaction is very different. Cyanide isn't involved in the rate determining step in the reaction of bromotriphenylmethane with cyanide. The rate determining step is the ionization to the triphenylmethyl carbocation. What does that mean? In this case, you double the concentration of bromotriphenylmethane, you double the rate. But what happens when you double the concentration of cyanide? Nothing. And so when the question was raised earlier, how do you know which way a reaction goes, whether it proceeds in 2 steps or whether it proceeds in 1 step? And I said, well, a very simple rule is a reaction at a tertiary halide center generally goes in 2 steps. That at a primary halide center generally goes in 1 step. Let me step back on that and ask the broader question, how did chemists learn this knowledge? Because it's easy to say, how do you know, meaning how do you study for an exam? But the harder question is, how do we derive knowledge? How do we derive knowledge is ultimately through experiment. And chemists observed. When they took compounds like ethyl iodide and they doubled the concentration in a reaction with cyanide, the rate doubled. They double the concentration of cyanide, the rate doubles. But very oddly, when you take a compound like bromotriphenylmethane, only the concentration of bromotriphenylmethane affects the rate. And so that's how that knowledge was acquired. All right, last thing I'll talk about is just the question that was raised before about what different factors affect the rate of reaction. All right, the biggest factor affecting rates is temperature. Higher temperature leads to more energy. More energy means that more molecules have enough energy to overcome the energy barrier of the rate determining step. And so you get a faster rate and a bigger K, a bigger rate constant.